Are we alone in the universe? This ancient question echoes across the vast, silent expanse of space. Tonight, we are going on a journey to answer it, traveling to 25 cosmic wonders where scientists believe alien life could be waiting. You will discover the most promising addresses in the galaxy, from hidden oceans in our own solar system to planets orbiting distant stars. We will visit worlds with skies of methane, wanderers drifting between the stars, and moons that fire geysers into the void. By the end, you'll know exactly where to look in the night sky and understand the real science behind humanity's greatest quest. Could life be floating in the acidic clouds of Venus? What mysteries lie beneath the frozen crust of a distant moon? The universe is not just a collection of stars, it is a gallery of possibilities, each more astonishing than the last. What kind of alien world do you hope is out there? Our journey begins in the cosmic neighborhood next door, a mere 4.2 light-years away. A world called Proxima Centauri b orbits a faint crimson star. This is not a distant point of speculation. It is the closest known exoplanet to our solar system, a world with a mass strikingly similar to Earth's, and it sits squarely within its star's habitable zone. That is the region where temperatures are just right, where a planet could theoretically have liquid water pooling on its surface. Imagine an ocean under an alien sun, a permanent, deep red twilight hanging in the sky. The possibility is breathtaking, but this neighborhood comes with dangers. Its sun, Proxima Centauri, is a red dwarf, a type of star known for its violent temper. It frequently erupts with monstrous stellar flares, blasts of radiation that could strip away a planet's atmosphere and bathe its surface in deadly ultraviolet light. So the question for Proxima b is one of survival. Does it possess a strong magnetic field to deflect those flares? Could a thick atmosphere shield any potential life? Or perhaps life there, if it exists, has found a way to thrive underground or in deep, shielded oceans. Its incredible proximity makes it our #1 target. Projects like Breakthrough Starshot envision sending tiny, laser-propelled probes there within a human lifetime. Our telescopes are already straining to catch a glimpse of its atmosphere, searching for the chemical fingerprints of oxygen, methane, or other biosignatures. Proxima Centauri b is our first, closest answer to the question of other Earths. It is a world of profound contradiction, a potentially habitable planet orbiting a hostile star, and it teaches us that the search for life is never simple. But while Proxima b is a solitary neighbor, the next stop on our list is a bustling family. Less than 40 light-years away, the TRAPPIST-1 system is a revelation. It is not just a star with one promising planet. It is a star with 7, each one roughly the size of our own Earth. All 7 of these worlds orbit an ultra-cool dwarf star, a faint, long-lived ember that bathes its planetary family in a gentle, perpetual twilight. 3 of these siblings, planets E, F, and G, are the true prizes. They sit snugly within the star's habitable zone, a trio of Earth-sized marbles in the cosmic sweet spot. The dynamics here are unlike anything in our solar system. These planets are incredibly close together, orbiting their star in a tight, harmonious dance. If you are standing on the surface of TRAPPIST-1e, you might look up and see its neighboring worlds, F and G, hanging in the sky as large, distinct orbs, perhaps even showing visible features like continents or clouds. Their proximity creates fascinating possibilities for life. The gravitational tug of war between these close-packed worlds could generate immense tidal heating, flexing their interiors and potentially powering volcanic activity or keeping subsurface oceans liquid far beyond the reach of their star's faint light. This means life might not need the sun's warmth at all. It could thrive in the dark, heated from within. The greatest gift of the TRAPPIST-1 system, however, is its invitation to science. Because these planets transit or pass in front of their star from our viewpoint, we can study their atmospheres. The James Webb Space Telescope is already turning its golden eye toward them, searching for the chemical whispers of water vapor, methane, or ozone. With 7 similar-sized targets so close together, we have a unique laboratory. We can compare and contrast their atmospheres, asking why one might have held onto its air while another lost it. The TRAPPIST-1 system is not just a candidate for alien life. It is a masterclass in planetary science, a compact archive of possibilities showing us that where one Earth-sized world might be a miracle, 7 together could be a pattern. Yet the TRAPPIST-1 system orbits a dim, cool star, a far cry from our brilliant sun. For a world that feels truly familiar, we must look farther. 1,400 light-years away, orbiting a star almost identical to our own, is Kepler 452b. Astronomers call it Earth's cousin, and for good reason. Its orbit around its yellow G-type star is 385 days, just 20 days longer than our own year. It receives a similar amount of light and warmth, placing it firmly in the habitable zone. The star it circles is a near twin of our Sun in size and temperature. This is not a planet clinging to a volatile red dwarf. It is a world in a stable, sun-drenched environment that could have lasted for billions of years. In fact, that is the most profound detail about Kepler 452b. It is old. This planet is roughly 6 billion years old, 1.5 billion years older than Earth. Think about what that means. If life emerged there at a similar pace to life on Earth, it has had an extra 1.5 billion years to evolve. On our world, that span of time covers the entire journey from single-celled organisms in the oceans to the civilization that built the telescope that found this planet. What could an intelligence achieve with a billion-year head start? The possibilities are staggering. This extended timeline is its greatest mystery and its most tantalizing promise. A stable, sun-like star provides a gentle, consistent energy source for eons, allowing for the slow, patient work of evolution and perhaps technology. Kepler 452b represents a vision of a mature Earth, a planet that has weathered its early cosmic storms and settled into a long, potentially life-nurturing autumn. It asks us a profound question: is life around stars like ours the rule, or are we the exception? Finding a world in such a familiar configuration tells us that our solar system is not a bizarre cosmic accident. It suggests that the ingredients for an Earth-like story are scattered throughout the galaxy, and on some of those worlds, the story may have reached a chapter we can scarcely comprehend. But a cousin 1,000 light-years away is still a distant dream. For a world we can touch, we must look much closer, to a rusty horizon we have already begun to explore. Mars, our red neighbor, has long been seen as a dead world, yet we are now discovering it is a world of profound and lingering whispers. The evidence is etched across its surface. Orbital images reveal the unmistakable scars of ancient riverbeds, vast deltas where water once flowed freely into long-vanished seas. These are not subtle hints. They are the geological ghosts of a planet that was once blue and wet, a place where conditions could have been ripe for life to emerge billions of years ago, just as it did on Earth. The question is no longer if Mars had the right ingredients. We see them in the clay minerals and sedimentary layers. The question is whether life ever took hold in those ancient streams. And even more astonishingly, whether it still clings to existence today, hidden from the harsh surface. Recent discoveries point to this incredible possibility. Orbiting radar has detected what appear to be lakes of liquid, briny water buried deep under the southern polar ice cap. On sun-facing slopes, strange dark streaks called recurring slope lineae appear and fade with the seasons, potentially caused by seeps of salty water just below the surface. These are not oceans, but they are potential refuges. In these damp, dark, salty pockets shielded from radiation, microbial life could, in theory, persist. This is why our robots are there, acting as our mechanical geologists. The Perseverance rover is right now navigating the dried-up delta of Jezero Crater, an ancient lakebed, drilling core samples of the most promising rocks. Its mission is to collect these Martian tubes of soil and rock, sealing them for a future spacecraft to bring back to Earth. A Mars sample return would be one of the most ambitious scientific endeavors in history, allowing scientists in terrestrial labs, with instruments far more powerful than any rover can carry, to search for the fossilized remains of ancient microbes. They will look for the molecular building blocks of life, for patterns in the rock that only biology can create. Mars teaches us that a world does not have to be a lush, tropical paradise to host life. It can be a cold, dry, and radiation-scarred desert, holding its secrets in the deep ice and the dusty memories of river stones. The hunt on Mars is a forensic investigation, a search for clues in a cold case that is over 3 billion years old. And we are finally gathering the evidence. Mars shows us that life can be a tenacious survivor in a harsh world. But what about a world where the ocean is not a memory, but a present-day reality, hidden just out of sight? Venture past the asteroid belt to the king of planets, Jupiter, and behold its moon, Europa. From a distance, it is a cracked, white marble streaked with rusty red lines, a frozen ball of ice. Yet this ice is merely the roof. Beneath a shell perhaps 10 to 15 miles thick churns a global, saltwater ocean containing more than twice the volume of all the water in Earth's seas combined. Imagine an entire world with a liquid heart completely sealed under a frozen sky. The energy to keep this vast ocean from freezing solid does not come from the sun, which is a distant, feeble speck here. It comes from Jupiter itself. As Europa orbits the massive planet, the relentless gravitational pull of Jupiter and its other large moons constantly flexes and kneads Europa's interior. This tidal friction generates immense heat, melting the ice from within and likely creating a dynamic, churning sea. But the promise of Europa goes deeper than just a lot of water. On the floor of this dark, alien ocean, scientists believe there could be hydrothermal vents, much like the ones found in the deepest trenches of Earth's oceans. On our planet, these vents are oases of life in the absolute darkness. They spew mineral-rich, superheated water, and around them thrive entire ecosystems of bizarre creatures, from giant tube worms to blind shrimp, all powered not by sunlight but by chemical energy from the planet's core. Europa's rocky seafloor, heated by that same tidal friction, could host these exact same kinds of vents. This means Europa possesses all the ingredients we believe are essential for life. Liquid water, a source of chemical energy, and organic molecules likely delivered by comet impacts. Life there would exist in perpetual darkness, possibly clustered around volcanic vents on the ocean floor, a biosphere completely independent of any star. We are not waiting long to learn more. The Europa Clipper mission, set to launch soon, will conduct dozens of close flybys using its suite of instruments to map the ice shell, probe the ocean's depth and salinity, and even sniff the faint plumes of water vapor that occasionally erupt from cracks in the surface, sampling the ocean without ever touching down. The ultimate dream, of course, is a lander that could one day melt or drill through that icy crust to directly taste the waters below. Europa transforms our understanding of where life can exist. It tells us that a warm, rocky core and a global ocean sealed beneath ice might be a more common recipe for life in the cosmos than a sunny, Earth-like surface. It is a water world waiting for us to say hello. Europa's hidden ocean is a profound secret, but one of its cosmic cousins is shouting its mysteries into the void. Orbiting the ringed giant Saturn is a small, brilliant world of ice named Enceladus. For years, it was considered just another frozen moon, a mere speck beside its larger siblings. Then the Cassini spacecraft arrived and witnessed something impossible. From the moon's south pole, gigantic geysers were erupting, shooting towering plumes of water vapor, ice particles, and organic molecules hundreds of miles into space. This was not a dormant world. Enceladus was alive with geological activity, actively venting the contents of its hidden subsurface ocean directly into the vacuum. Cassini did not just take pictures. On several daring passes, it flew directly through these glittering plumes, tasting their composition with its onboard instruments. The data revealed two astonishing clues. First, the plumes were salty, like Earth's oceans. Second, they contained tiny particles of silica, a mineral that, on our planet, only forms in specific conditions. Specifically, when hot water around 90 degrees Celsius interacts with rock. This was the smoking gun. The silica nanoparticles pointed to hydrothermal vents on the floor of Enceladus's ocean, where superheated, mineral-rich water was surging up through a rocky seabed. Here, then, was the recipe, not just theorized but sampled. A global liquid water ocean heated by Saturn's tidal forces, churning above a rocky core where hydrothermal chemistry could provide both the energy and the building blocks for life. And unlike Europa, where the ocean is locked under miles of ice, Enceladus is handing us its secrets on a silver platter. Those continuous, accessible plumes are like a free sample delivery service from the depths of an alien sea. A future mission could fly through them with instruments far more advanced than Cassini's, to analyze complex organic molecules and even look for potential signs of biological activity. It could search for amino acids in specific patterns or imbalances in chemical ratios that life leaves behind. Enceladus presents us with a staggering opportunity. We do not need to land, drill, or melt our way in. The ocean is coming to us, offering its contents up for examination. This tiny, energetic moon has rewritten the rules, proving that some of the most habitable real estate in our solar system may be on small, ice-covered worlds with enormous, generous hearts. The plumes of Enceladus offer a direct taste of a hidden sea, but Saturn has another moon that presents an entirely different vision of a living world. Titan is a place of profound and eerie familiarity, wrapped in a thick, hazy orange atmosphere of nitrogen, the only moon in our solar system to boast such a substantial cloak of air. Stand on its surface and the sky would feel heavy, the gravity light, and the temperature a cryogenic -290 degrees Fahrenheit. Yet look around and you would see a landscape that hauntingly mirrors our own. Titan has rolling dunes not of sand but of dark, organic hydrocarbons. It has mountains of water ice hard as rock in the deep cold. Most astonishingly, it has a full, active hydrological cycle just like Earth. But here, the rivers are not filled with water. They flow with liquid methane and ethane. These hydrocarbons pool into vast lakes and seas near the poles, some larger than North America's Great Lakes. The rain that falls from Titan's smoggy skies is not water, but a slow drizzle of liquefied natural gas. This is a world built from an entirely different chemistry book, and it forces us to ask a radical question. If life can emerge in the warm, watery pools of Earth, could a different kind of life, a weird life, arise in the frigid methane lakes of Titan? Astrobiologists call this the possibility of a methane-based biosphere. Instead of water as its solvent, a Titanian organism might use liquid methane. Instead of breathing oxygen, it might metabolize hydrogen or acetylene, drawing energy from chemical reactions we would find utterly inert. Its cells would need to be built from molecules that remain flexible at temperatures where water is a solid stone. This is not science fiction. It is a serious scientific hypothesis based on the bizarre but abundant chemistry we have observed. The Hycean probe, which landed on Titan in 2005, sent back images of a rounded, cobbled landscape, likely shaped by fluid flow, and detected a rich soup of organic molecules in the atmosphere, the very building blocks that, on a warmer world, might assemble into life. Beneath this alien surface, however, lies another secret. Scientists strongly suspect Titan harbors a vast subsurface ocean of liquid water, much like Europa and Enceladus, kept liquid by tidal heating from Saturn. This means Titan could potentially host two separate and utterly alien biospheres. One, a weird surface life based on methane chemistry, and another, more familiar water-based life in the dark ocean below, never aware of the other's existence. To unravel these mysteries, we are sending a revolutionary explorer. The Dragonfly mission is not a rover. It is a nuclear-powered rotorcraft, a large drone designed to fly across Titan's dense atmosphere. It will leapfrog from one intriguing site to another, sampling the complex organic chemistry of the dunes and dry lake beds, searching for the chemical signatures of probiotic processes or even life itself. Dragonfly will land near the equator and eventually aim for the Selk impact crater, a site where liquid water may have once mixed with surface organics in a transient warm event. Titan is more than a moon. It is a parallel experiment in planetary evolution, a looking-glass world that shows us life, if it exists, might not just be in the next star system. It could be dressed in a completely alien biochemistry, thriving in the freezing rivers of a moon in our own celestial backyard, waiting for a drone to buzz through its orange haze and discover it. Venus stands as a stark warning of a runaway greenhouse effect, its surface hot enough to melt lead under an atmosphere of crushing carbon dioxide. For decades, it was written off as a sterile, hellish counterpoint to Earth. Then, in 2020, a team of astronomers announced a discovery that turned this entire narrative on its head. They detected the spectral signature of phosphine gas high in the Venusian cloud decks. On Earth, phosphine is a molecule almost exclusively made by industrial processes or by anaerobic microbes thriving in oxygen-free environments like swamps and animal guts. Finding it in the temperate zone of Venus clouds, where pressures and temperatures are surprisingly Earth-like, was a profound shock. It was a whisper of biology in a place we had declared dead. The scientific community erupted in debate. Could there be non-biological sources like unknown volcanic chemistry or exotic atmospheric reactions? Subsequent studies have both challenged and supported the original finding, leaving the question tantalizingly open. This controversy, however, has reignited a brilliant and strange hypothesis. 50 kilometers above the scorching surface, the cloud layers of Venus are a potential oasis. The temperature is a mild 30 degrees Celsius and the pressure is similar to that at sea level on Earth. The catch, of course, is that these clouds are not made of water vapor. They are composed of concentrated sulfuric acid, a substance that would dissolve most life as we know it. Yet extremophiles on Earth thrive in acidic hot springs and mine tailings. Could a form of microbial life have evolved a protective shell or biochemistry to survive and even float in this aerial ocean of acid? These hypothetical Venusian microbes would not live on the surface. They would be aerial plankton drifting in a perpetual global haze, their life cycle tied to the droplets that make up the clouds. To settle this extraordinary mystery, we are going back. Upcoming missions like DOVINCI+ will send a descent probe plunging through the atmosphere, analyzing its composition layer by layer with unprecedented precision, hunting for that phosphine and other complex molecules. The VERITAS orbiter will map the planet's surface geology in detail, searching for signs of active volcanism that could provide a non-biological source for the gas. Venus now represents the ultimate cosmic paradox. It is a world that shows us the terrifying potential of climate catastrophe, while simultaneously hinting that life might be tenacious enough to find a foothold not on the ground but in the sky. It forces us to ask if a planet can be both a cautionary tale and a sanctuary, its secrets floating just out of reach in a corrosive, golden haze. The skies of Venus hold a toxic mystery, but to find a world bathed in the light of 3 suns, we must travel much farther. 32 light-years away, in the constellation of Scorpius, orbits a planet called GJ667cc. This is a super-Earth, a world with a mass at least 3.4 times that of our own, and it sits squarely in the habitable zone of its star. But this is no ordinary star. It is part of a triple star system, a cosmic ballet of 3 suns dancing together. From the surface of this planet, you might look up and see not 1, but 2 or even 3 distinct points of light in the sky, a permanent, spectacular sunset of orange and red hues. The primary star it orbits is a small, cool M-dwarf, but the other 2 stars in the system are close enough to appear as brilliantly bright companions. This complex gravitational environment makes its stable orbit all the more remarkable. For a planet to maintain a steady, circular path in a system with multiple stars pulling at it is a delicate feat, suggesting a peaceful and enduring cradle for potential life. Another crucial detail about this system is its metallicity, a term astronomers use to describe how rich a star is in elements heavier than hydrogen and helium. The stars of the JWST system are metal-rich, meaning they were formed from a cloud of gas and dust packed with the iron, silicon, carbon, and oxygen necessary to build rocky planets. This planet did not form from spare parts. It was built from a well-stocked cosmic warehouse of the very materials that make up our own world. The promise of JWST, however, comes with a significant caveat. Because it orbits so close to its dim red dwarf star to stay warm, it is almost certainly tidally locked. Just as our moon always shows the same face to Earth, one side of this super-Earth would permanently face its sun, locked in eternal daylight, while the other side is shrouded in perpetual frozen night. This creates a world of extreme contrasts. The day side could be scorching, while the night side is lethally cold. But between these 2 extremes, in the thin ribbon of twilight at the terminator line, conditions might be just right. Here, along the border of day and night, temperatures could be moderate enough for liquid water to exist. Furthermore, a thick atmosphere could work as a global heating blanket, redistributing heat from the hot side to the cold side, potentially creating a planet-wide temperate zone. Life on such a world might huddle in the eternal dawn or dusk, or perhaps float in the atmosphere above the scorching day side. JWST challenges our Earth-centric views of habitability. It shows us that a stable, metal-rich environment can exist even in a complex stellar family, and that a planet need not spin to be alive. It might simply stand still, presenting one face to its suns and holding its secrets in the delicate balance between fire and ice. The search for life often focuses on delicate balances, but some worlds are built from sturdier stuff. LHS 1140b is a super-Earth of remarkable promise, a dense, rocky giant orbiting a star just 49 light-years away. Its mass is nearly 7 times that of our own planet, making it a heavyweight in the rocky planet category. What makes this world so compelling is not just its location in the habitable zone of its small, dim red dwarf star, but the exceptional calm of that star itself. Unlike the flare-prone violence of Proxima Centauri, this star is quiet and stable, a gentle parent that has likely not stripped away the atmospheres of its children with violent outbursts. This tranquility is a game-changer. It means LHS 1140b has had a peaceful, billion-year history where a thick atmosphere, if it ever formed, could have persisted, creating a stable climate capable of nurturing oceans or lakes. The planet's density tells us more about its story. Measurements suggest it is not a puffy mini-Neptune made of gas. It is almost certainly a rocky world, but with a twist. Its incredible density hints at a composition rich in iron, possibly harboring a massive metallic core far larger than Earth's. This could give the planet a strong magnetic field, a planetary shield that would further protect any atmosphere from the steady stellar wind. And here is the best part for astronomers. LHS 1140b transits. It passes directly in front of its star from our vantage point, causing a tiny, predictable dip in starlight. This transit is a scientific gift. It allows our telescopes, especially the James Webb, to perform a technique called transmission spectroscopy. as the star's light filters through the thin ring of the planet's atmosphere during these transits, specific molecules absorb certain colors of light. By analyzing this filtered starlight, we can read the chemical barcode of the atmosphere itself. We can search for the telltale signs of water vapor, carbon dioxide, methane, or even the artificial markers of a technological civilization. This combination is rare and powerful. A large, rocky world in the habitable zone of a quiet star, offering us a clear window into its air. LHS 1140b is not a fragile maybe. It is a substantial, well-defended candidate, a fortress world that may have successfully guarded the conditions for life across cosmic eons, now holding its breath as our telescopes learn to read its story in the light. Yet the quest for a true Earth twin leads us back to one of the first worlds that captured our collective imagination. Over 600 light-years away, orbiting a star remarkably similar to our own Sun, is Kepler 22b. It was one of the Space Telescope's earliest and most celebrated discoveries, the first confirmed planet found orbiting comfortably within the habitable zone of a Sun-like star. The initial announcement sparked visions of a blue marble, a second Earth basking in familiar sunlight. But as we have studied it more, Kepler 22b has become a deeper, more complex mystery. We know its radius is about 2.4 times that of Earth, placing it in a category we call a super-Earth or a mini-Neptune. That size is the key to the puzzle. A planet of that scale could be several very different things. It might be a massive, rocky world with a thin atmosphere, a super-Earth with continents and oceans. It could be a gaseous planet with a thick hydrogen and helium envelope, a mini-Neptune with no solid surface at all. Or, most intriguingly, it might be something entirely new to our experience, a water world. Imagine a planet with little to no land, just a global, endless ocean hundreds of miles deep, capped by a thick, steamy atmosphere. The pressure at the bottom of such an ocean would be crushing, creating exotic forms of ice not from cold but from immense pressure, a solid seafloor of hot ice. This is where a fascinating hypothesis comes in, the concept of Hycean worlds. The name blends hydrogen and ocean. These are planets with a substantial atmosphere rich in hydrogen, enveloping a vast, globe-spanning liquid water ocean. On the surface, such a world would be a dark, hot, and pressurized place, utterly inhospitable to life as we know it. But within that deep, global ocean, shielded from the hostile surface conditions, there could be an environment stable enough for chemistry to become biology. The hydrogen-rich atmosphere above would create a tremendous greenhouse effect, trapping heat and potentially keeping the ocean liquid even far from the star's warmth. More importantly, that atmosphere could dissolve into the ocean's upper layers, providing a rich chemical soup for reactions. Scientists speculate that in the eternal darkness of a Hycean ocean, microbial life could thrive around chemical energy sources, much like the organisms at Earth's deep-sea vents, completely independent of sunlight. Kepler 22b might be one of these strange aquatic globes. Its size and estimated mass leave the door wide open to this possibility. It represents a crucial lesson in our search. Not every habitable world will look like home. Some might be shrouded in perpetual steam, their entire biosphere hidden beneath a crushing global sea and a poisonous sky. A reminder that life's true canvas may be far stranger and more diverse than we ever dared to dream. But a single planet story is just one piece of a much larger cosmic map. To understand our true place in the universe, we must zoom out far beyond our solar system, beyond even the local stars, to view our entire galaxy as a single, sprawling metropolis. This brings us to a profound and humbling concept, the galactic habitable zone. It is the idea that not all neighborhoods in a galaxy are created equal for nurturing complex, long-lived life. Just as a planet must orbit within its star's Goldilocks zone for liquid water, a solar system must reside in the galaxy's sweet spot for safety and stability. The center of the Milky Way is a dazzling, dangerous downtown. It is packed with stars, a brilliant, crowded core where the density is so high that nighttime would be an endless twilight. But this comes at a terrible cost. The sheer number of stars means supernova explosions are far more frequent, catastrophic events that can sterilize entire swaths of space with lethal radiation. Even more ominously, at the very heart lies a supermassive black hole, Sagittarius, a star, whose gravitational tantrums can fling deadly radiation across thousands of light years. This is no place for a fragile biosphere to develop over billions of peaceful years. On the other hand, venture out to the galaxy's sparse, quiet outer rim. Here, the danger from neighbors diminishes, but a different poverty sets in. These regions formed from primordial gas that was poor in heavy elements, the metals like iron, silicon, and carbon that are the essential building blocks of rocky planets and life itself. A star born out here might not have enough solid material to form Earth-like worlds at all. So where is the safe, prosperous middle ground? We are living in it. Our solar system orbits about halfway between the crowded center and the empty fringe, in a relatively calm spiral arm. We are in the galactic suburbs, a region rich enough in heavy elements to forge our planet, yet quiet enough to avoid frequent stellar catastrophes. This privileged position allowed Earth 4.5 billion years of relatively uninterrupted evolution. The question this concept forces us to ask is staggering. Are such galactic habitable zones rare? In a galaxy of hundreds of billions of stars, perhaps only a small percentage orbit within this narrow band of safety and abundance. And when we look at other galaxies, warped by collisions or blazing with furious star formation, their peaceful suburbs might be even harder to find. Our address in the Milky Way may be more special than we ever realized, a quiet street in a safe neighborhood on the outskirts of a city of stars, offering the perfect cosmic cradle for a story like ours to unfold. K218b is a name that will be etched in the history of our cosmic search. 120 light-years away, this world orbits a cool red dwarf star, and for years it was catalogued as just another super-Earth, a planet larger than ours but smaller than Neptune. Then the James Webb Space Telescope turned its gaze upon it, and the data revealed something extraordinary. In the hazy atmosphere of this distant world, Webb detected the unmistakable signatures of carbon dioxide and methane. These are carbon-bearing molecules, the very stuff of organic chemistry, and they were found in the atmosphere of a planet firmly within its star's habitable zone. This was not proof of life, but it was a profound revelation. It told us that the basic chemical ingredients for life, as we understand it, are present and active on a world far beyond our solar system. K218b, however, is no Earth twin. It is a world that embodies a radical and fascinating hypothesis, the concept of the Hycean world. The name comes from blending hydrogen and ocean, and it describes a planet with a thick, extended atmosphere rich in hydrogen, enveloping a vast global liquid water ocean that could be dozens or even hundreds of miles deep. Imagine a planet with no continents, no shorelines, just an endless, dark sea stretching from pole to pole beneath a sky of dense, warm hydrogen. The surface of such an ocean would not be a pleasant place. The atmospheric pressure would be immense, crushing, and temperatures could be hot enough to boil water, kept liquid only by the overwhelming weight of the atmosphere itself. Yet, it is in the depths below this hostile surface where the promise for life truly lies. Descend through the murky, warm upper layers, and you might reach a region where pressures and temperatures become more moderate, a deep, dark abyss where a stable aquatic environment could exist for billions of years. In this eternal night, life would have no use for sunlight. Instead, it could draw energy from the chemical gradient between the hydrogen-rich atmosphere dissolving into the ocean and minerals from a rocky core below. Or hydrothermal vents on the seafloor could provide warmth and chemical nourishment, just as they do on Earth. The life that might evolve here would be truly alien, adapted to pressures we can scarcely replicate and a chemistry built around hydrogen. K2-18b, with its detected methane and carbon dioxide, fits the profile of such a world perfectly. These gases could be byproducts of geological activity, or they could be the waste products of a vast global microbial biosphere thriving in the dark ocean. Webb's future observations will hunt for another molecule, dimethyl sulfide, which on Earth is only produced by life. Finding it there would be a seismic event. Hycean worlds force us to expand our imagination of what a living planet can be. They are not gardens under a friendly sun. They are pressurized aquatic globes shrouded in primordial gas, where the entire story of biology might be written in the silent, dark currents of a planet-wide sea. A world of fire, not ice, awaits us at Jupiter's doorstep. Io is the solar system's antithesis to Europa, a moon so violently active it makes our most explosive volcanoes look like campfires. This is the most volcanically intense body we have ever seen. Its surface a cracked and sulfur-stained canvas painted fresh daily by hundreds of erupting vents. The energy for this perpetual inferno comes from the same source that warms Europa's ocean, but with a catastrophic twist. Jupiter's immense gravity, combined with the rhythmic tug of its other large moons, flexes Io's interior like a ball of clay squeezed in a giant's fist. This tidal heating is so extreme it melts rock, creating vast global seas of magma just beneath a thin, brittle crust. Io is quite literally being cooked from the inside out. For decades, this hellscape was written off as a sterile crucible, a place where the very concept of life seemed laughable. Yet, as we have discovered life thriving in Earth's own most punishing environments, a daring question has emerged. Could Io's fury itself be a cradle? The speculative theories point to the moon's own unique refuges. Deep within the crust, where the molten rock meets solid ground, there could be vast subsurface magma chambers. Around the margins of these chambers, where superheated rock meets cooler material, temperatures might drop into a range that certain Earth-based extremophiles called thermophiles could theoretically withstand. These are microbes that thrive in near-boiling water in volcanic hot springs and deep-sea hydrothermal vents. On Io, such organisms would not rely on water or sunlight. Their entire biochemistry might be built around sulfur, an element that is abundant and energetically rich in Io's volcanic plumes. They could metabolize sulfur compounds, drawing energy from the chemical disequilibrium between the molten interior and the solid crust. An even more exotic possibility floats in the plumes themselves. When Io's volcanoes blast material hundreds of miles into space, that material includes water vapor, sulfur dioxide, and simple salts. In the fleeting moments within an ascending plume, protected from the hard vacuum of space by the erupting gases themselves, could simple, hardy spores or microbial life exist. It would be a transient, aerial existence, constantly falling back to the deadly surface, only to be launched again by the next eruption. While the odds are astronomically long, Io forces us to confront the sheer stubbornness of life's potential. It expands the habitable zone from a region of comfortable temperatures to include pockets of raw chemical energy, even within a world of perpetual fire. If life can cling to existence here in the roof of a planetary furnace, then the definition of a living world becomes almost limitless. The concept of a planet without a sun seems like the ultimate cosmic dead end, a frozen tomb drifting in perpetual night. Yet our next wonder shatters that assumption entirely. These are rogue planets, worlds violently ejected from their young star systems by gravitational chaos, cast adrift to wander the interstellar darkness alone. They are cosmic orphans, untethered from any sun, and for decades we believed they must be barren, frozen wastelands, but a revolutionary idea has emerged from the cold. What if these lonely wanderers are not dead, but sleeping giants, harboring secret oceans of life beneath their surfaces? The key lies in a thick, insulating blanket. A rogue planet with a massive atmosphere of hydrogen could act as a phenomenal insulator, a planetary thermos, while the surface would be unimaginably cold, approaching absolute zero. The immense pressure of that atmosphere traps heat rising from the planet's interior. This internal warmth does not come from a star. It comes from the slow, steady decay of radioactive elements like uranium and thorium in the planet's rocky core, the same process that helps heat Earth's interior. On a large, rocky super-Earth, this geothermal heat could be substantial, persisting for billions of years. If the atmospheric blanket is thick enough, it could create a greenhouse effect so powerful that the heat cannot escape, creating a stable, warm layer deep beneath the ice and clouds. There, trapped between the frozen surface and the warm rock below, a global subsurface ocean of liquid water could persist in absolute darkness. This is not a temporary puddle. It could be an ocean larger than all of Earth's seas combined, sealed away for eons. Within that sunless sea, life could find a way. The most likely oasis would be on the ocean floor at hydrothermal vents. Just as on Earth's seafloor, water seeping down through cracks in the rocky crust would be superheated by the planet's internal warmth, then spew back out, rich with dissolved minerals like sulfides. This chemical disequilibrium is a potent source of energy. Around these vents in the eternal, starless dark, entire ecosystems could theoretically thrive. They would be biospheres of pure chemistry, where the entire concept of day and night, summer and winter is meaningless. The only rhythm would be the slow pulse of geothermal heat and the steady flow of mineral-rich plumes. These organisms would never know a sun had ever existed. Their entire universe would be the dark water, the warmth from below, and the chemical energy that fuels their existence. Finding such a world, however, is a monumental challenge. Rogue planets emit no light of their own and are incredibly difficult to detect. We spot them only rarely when their gravity briefly magnifies the light of a distant background star, an event called microlensing. Each detection is a precious clue. The upcoming Nancy Grace Roman Space Telescope is designed to find thousands of these nomads through microlensing surveys, giving us our first statistical understanding of how common they are. The existence of life on a rogue planet would be the ultimate testament to life's tenacity. It would prove that a star is not a requirement for biology, that the engine of life can be a planet's own radioactive heart, beating slowly in the infinite cold. These lonely wanderers could be the most common habitable real estate in the entire galaxy, dark ocean worlds sailing silently between the stars, each one a closed, complete, and independent universe. The dark ocean worlds between the stars are a profound possibility, but we have not even finished searching our own cosmic backyard. Within the asteroid belt, a region we once thought was just a field of dry rock and rubble, hides a world that defies expectation. Ceres, the largest object in the belt, is officially classified as a dwarf planet, and data from the Dawn spacecraft revealed it is anything but a dead rock. Its surface is dotted with mysterious, brilliant white spots, the most famous cluster sitting in the Ocata crater. Spectroscopic analysis solved one mystery, only to create a far greater one. Those bright spots are not ice. They are vast deposits of sodium carbonate, a kind of salt you would find in a drying lakebed on Earth. This material did not come from the surface. It was brought up from below, a sign of recent geological activity. The leading theory is that Ceres possesses a deep, briny subsurface layer, a reservoir of saltwater mud or a localized aquifer. Millions of years ago, perhaps even more recently, an impact fractured the crust and this salty slush oozed upward, erupting in a weak, icy cryovolcano. When the water ice sublimated away into space, it left behind this glaring, salty residue. This suggests Ceres is a geologically active world with a liquid, or at least a soft, muddy layer, separated from its rocky core by a shell of ice. Where there is liquid water, salts for chemistry, and internal heat, the basic prerequisites for life are intriguingly present. This expands our search from moons of giant planets to the dwarf planets themselves. Far beyond Ceres, in the frozen depths of the Kuiper belt, Pluto continues to astonish us. Data from the New Horizons flyby showed a world of shocking complexity, with nitrogen glaciers, water ice mountains, and a vast heart-shaped plain called Sputnik Planitia. The location and geology of this basin strongly suggest Pluto has a subsurface ocean of liquid water, kept from freezing by the decay of radioactive elements in its core and the insulating effect of a thick layer of exotic ices. If true, Pluto joins the growing list of ocean worlds, and if Pluto has an ocean, how many other dwarf planets and large Kuiper belt objects might as well? Worlds like Eris, Makemake, and Haumea are all large enough to retain internal heat. The Kuiper belt, once seen as a freezer full of inert relics, may in fact be a sprawling archipelago of hidden aquatic globes, each a potential incubator for simple subsurface life. Ceres and Pluto teach us a humbling lesson. Habitability is not a privilege reserved for planets orbiting stars at a perfect distance. It can emerge in the most unexpected places, in the muddy heart of an asteroid belt dwarf, or in the dark, radioactive warmth beneath the frozen surface of a world on the solar system's ragged edge. The building blocks of life, it seems, were delivered everywhere, and where even a little heat and a little water meet, the possibility quietly stirs. The quiet, ancient glow of Tigodon's star offers a different kind of promise. A mere 12 light-years away, this faint, ultra-cool red dwarf is a stellar elder, burning calmly for at least 8 billion years. Orbiting this patient sun are two of the most Earth-like worlds we have ever found, Tigodon's star B and C. Both are rocky planets with masses incredibly close to our own, and both reside within their star's optimistic habitable zone where liquid water could exist on their surfaces. This system presents a vision of profound stability. For billions of years longer than our solar system has existed, these two worlds have basked in the gentle, unchanging light of their old, quiet star, free from the violent flares that plague younger red dwarfs. They have had an almost unimaginable amount of time for chemistry to become biology, and for biology to evolve into complexity. The dynamics here are intimate. These two Earth-mass planets orbit incredibly close to their star and to each other, completing their years in just 4.9 and 11.4 Earth days respectively. From the surface of one, the other would appear as a large, brilliant companion in the sky. Their proximity creates a fascinating possibility, one that echoes a theory about our own early solar system. When planets orbit so closely together, material can be exchanged. A large asteroid impact on Tigodon B could blast rocky debris into space, and some of that debris, carrying potential microbial hitchhickers shielded within the rock, could be captured by the gravity of Tigodon C, landing on its surface millions of years later. This process, called lithopanspermia, could theoretically seed life from one world to its neighbor. If life arose independently on both, they would be separate experiments. But if it arose on just one, it might have used meteorites as a cosmic ferry, spreading a single genesis across two worlds. This twin system challenges our solitary perspective. Life on Earth may have begun in isolation, but around Tigodon's star, biology might have had a partner from the very beginning, a sister world in the same gentle bath of starlight, sharing its most profound secret across the void. Our search for alien worlds is a hunt for potential homes, but what if we are not alone in the act of searching? In 1977, a radio telescope in Ohio picked up a signal so powerful and so strange it drove an astronomer to scribble "wow." In the margin of the printout, it was a 72-second burst of intense, narrowband radio waves, precisely the kind of signal predicted to come from an artificial, technological source. It came from the direction of the constellation Sagittarius, and then it was gone. Despite decades of follow-up, the WOW signal was never heard again. It remains the most tantalizing, unexplained event in the history of listening for extraterrestrial intelligence. That singular event embodies the entire purpose of SETI, the search for extraterrestrial intelligence, a scientific endeavor that shifts our focus from places to signals. Instead of looking for habitable environments, SETI listens for technosignatures, deliberate or accidental broadcasts from a civilization advanced enough to build transmitters. This could be a focused radio beacon, a powerful laser pulse flashing like a cosmic lighthouse, or even the leakage from a planet's own television and radio broadcasts, signals that have been drifting away from Earth for over a century. The modern effort is more sophisticated than ever. Projects like Breakthrough Listen use some of the world's most powerful telescopes, scanning millions of stars across a wide range of radio and optical frequencies, processing more data in a day than earlier projects did in a year. They are listening for that needle in a cosmic haystack, a pattern that natural astrophysics cannot explain. The philosophical weight of this search is immense. A confirmed detection would answer humanity's oldest question in an instant, transforming our understanding of our place in the cosmos. It would tell us that intelligence is not a lonely fluke, but a possible feature of the universe. The wow signal, whether it was a one-time cosmic coincidence or a fleeting hello, reminds us that the greatest discovery in history might not be a planet, but a message waiting in the static between the stars. The wow signal reminds us that intelligence, if it exists, might announce itself. But what if we are looking for the wrong kind of announcement? Instead of a message, we could search for the shadow of a civilization so advanced its engineering reshapes stars. This is the hunt for technosignatures, and it begins with one of the most ambitious ideas in all of science fiction, the Dyson sphere. Proposed by physicist Freeman Dyson in the 1960s, it is not a solid shell, but rather a vast swarm of orbiting solar collectors, a civilization's ultimate power grid built around its own sun to capture every last photon of energy. A star wrapped in such a megastructure would present a bizarre signature to our telescopes. From the outside, the star itself would seem to dim or even vanish in visible light blocked by the swarm. But energy cannot be created or destroyed, only transformed. All that captured stellar energy must go somewhere. It would be irradiated as waste heat, glowing brightly in the mid-infrared spectrum. So astronomers scan the sky, not just for unusual radio signals, but for stars that are oddly dark in visible light, yet blazingly bright in infrared, objects that look like cosmic engines rather than natural suns. While no full Dyson sphere has been found, candidates like Tabby's star, with its strange, irregular dimming, have sparked intense debate, reminding us that nature can be as weird as any engineering. The signature of a civilization, however, might be far more subtle than a star wrapped in metal. Imagine pointing a powerful future telescope at the night side of an Earth like exoplanet. What if you saw not darkness, but a faint, shimmering grid of light? City lights, the collective glow of billions of street lamps, homes, and industries, could be detectable across interstellar distances, especially if they used efficient LED lighting that emits at specific, artificial colors. Another clue might float in the planet's air. Certain industrial chemicals like chlorofluorocarbons or artificial greenhouse gases with no natural source would persist in an exoplanet's atmosphere as a permanent chemical signature of industry. Detecting such pollutants would be a profound and sobering discovery, evidence of a civilization that has mastered its planet's chemistry for better or worse. We can even look closer to home, or rather, closer to other stars. A sufficiently advanced civilization might not just build around its star, but in the space around it. A dense swarm of satellites, like a supercharged version of our own communications constellations, could create a detectable technosignature. As the swarm orbits, it would cause a predictable, repeating pattern of tiny dips in the star's light, distinct from the smooth transit of a planet. Each pass of the swarm would create a faint, patterned shadow. This search fundamentally expands our definition of life in the cosmos. we are no longer just hunting for microbes in icy oceans or oxygen in alien air. We are hunting for intellect, for purpose, for the unmistakable fingerprint of a mind that has looked at the universe and decided to build something within it. The absence of such signatures is its own profound message, but their potential discovery would rewrite not just biology but history, telling us that intelligence, ambition, and engineering are also part of the universe's story. The fingerprint of a cosmic engineer may be the ultimate discovery, but the seeds of life might not need a mind to spread. They could be cosmic hitchhikers. This is the theory of panspermia, the idea that the basic ingredients for life, or even simple organisms themselves, can travel between planets and star systems, carried on asteroids, comets, or even microscopic dust grains. The evidence for this incredible journey begins in the cold, dark clouds between the stars. Radio telescopes have detected a rich soup of complex organic molecules floating in these interstellar nurseries, from simple sugars like glycolaldehyde to the ringed structures of aromatic hydrocarbons. These are not just random chemicals, they are the very precursors to amino acids and the nucleobases that form DNA and RNA. When a star and its planets form from such a cloud, these molecules are baked into the recipe from the very beginning, delivered to young worlds by a constant rain of comets and asteroids during the early, violent period of a solar system's life. We have seen this delivery service in action. Meteorites that have fallen to Earth, like the Murchison meteorite, contain a stunning array of these organic compounds, including over 70 different amino acids, many not commonly found on Earth. The building blocks of life are not rare, they are universal cargo shipped across the galaxy on rocky freighters, but could life itself survive such a trip? The answer may lie in some of Earth's toughest inhabitants, organisms known as extremophiles. We have found bacteria thriving in the boiling acid of volcanic pools, in the crushing pressures of the deep ocean, and most importantly for panspermia, frozen in permafrost and encased in salt crystals for millions of years. The most resilient of all might be tardigrades, microscopic water bears that can enter a state of suspended animation called cryptobiosis. In this state, they can survive the hard vacuum of space, intense radiation, and temperatures near absolute zero. Experiments on the International Space Station have proven that tardigrades attached to the outside of the station can survive direct exposure to the space environment for days. If a microscopic organism like this can be encased in rock, shielded from the worst radiation, the possibility opens up. A life-bearing rock blasted off a wet world like early Mars by a giant impact could, in theory, protect its microbial passengers for an interstellar journey lasting millions of years, eventually crashing into another habitable world like Earth, seeding it with life. This is lithopanspermia, the transfer of life via rocks, and it suggests our solar system could be a single, interconnected biological network. If life began on Mars first, we might all be Martians. This leads to the most speculative and profound twist on the idea, directed panspermia. What if the seeding was not accidental but intentional? Imagine an ancient, advanced civilization, perhaps facing its own world's demise, looking out at the galaxy. They could encode their genetic blueprint or even launch hardy, engineered microbes on protected probes toward promising young planets, a biological legacy cast across the stars. It is a staggering thought, one that connects every potential life-bearing world we have discussed into a single cosmic story. If true, life on Earth would not be a random accident in an indifferent universe, but a chapter in a deliberate saga of biological expansion written by ancestors we will never know. It transforms the galaxy from a collection of isolated experiments into a potential garden, cultivated by intelligence long before our sun even ignited. Whether by random chance or deliberate design, panspermia suggests a universe where life is not just tenacious but contagious, spreading its story one rocky fragment, one frozen spore at a time across the infinite dark. The promise of a planet in the habitable zone can be shattered by a simple, brutal fact of orbital mechanics. For many worlds orbiting the most common stars in the galaxy, the red dwarfs, a stable orbit comes at a steep price. These stars are so dim and cool that a planet must huddle very close to stay warm enough for liquid water. At such intimate distances, the star's gravitational pull becomes an irresistible force, gradually slowing the planet's rotation until it becomes tidally locked. One hemisphere permanently faces its sun, bathed in never-ending, scorching daylight. The opposite hemisphere is condemned to an eternal, frozen night, a dark side that never sees a sunrise. This creates a world of terrifying extremes, a planet split into two hostile kingdoms of fire and ice. For decades, this reality led astronomers to dismiss many of these promising worlds as hopelessly uninhabitable. How could life survive on a world where half the planet bakes and the other half freezes solid? The answer may lie in the narrow border between these two realms, a place of perpetual twilight called the Terminator Zone. Imagine standing on this planet's surface at the line where day meets night. The sun would hang permanently on the horizon, a fixed, unmoving beacon casting long, eternal shadows. This is not a place of sunset or sunrise. It is a permanent state of dusk or dawn, a band that encircles the entire globe. Here, in this thin ribbon of twilight, temperatures could theoretically be just right. The relentless heat of the day side bleeds into the frigid cold of the night side, moderated by the atmosphere and the planet's own geology. In this stable, temperate ring, liquid water could pool on the surface or exist in underground aquifers. Rivers might flow from the icy highlands of the night side, fed by glaciers that creep toward the warmth, melting as they cross into the Terminator's gentle light. The entire biosphere of such a world would be compressed into this circular strip, a band of life clinging to the edge of light and dark. Life in the Terminator Zone would face unique challenges and opportunities. Photosynthetic organisms would orient themselves permanently toward the low sun on the horizon, their growth patterns utterly unlike anything on Earth. The weather patterns would be bizarre and constant, with powerful winds howling from the hot day side to the cold night side, potentially circulating warmth and nutrients around the planet. A thick atmosphere would be absolutely essential, acting as a global heating blanket to redistribute heat and prevent the night side's atmosphere from freezing and collapsing onto the surface. With a robust atmosphere, the entire planet might be more temperate, but the Terminator would still be the most stable region. For a civilization emerging on such a world, their entire concept of time and direction would be built around this static sun. Their migrations, their agriculture, their very cities would be arranged along this narrow, habitable belt, with the blazing desert at their backs and the frozen wastes ahead. The Terminator Zone transforms a seemingly doomed planet into a world of profound possibility. It teaches us that habitability does not require a spinning globe with a regular day-night cycle. Life is an opportunist, and on a tidally locked world, its only opportunity is a permanent sunset, a line drawn in the sand between two extremes, where the conditions for existence are forged in a delicate, eternal balance. Europa and Enceladus are not solitary miracles. They are part of a growing family, revealing a pattern so profound it reshapes our entire view of the solar system. Around the gas giants Jupiter and Saturn, a host of other icy moons are now suspected of hiding their own secret seas. Jupiter's giant moon Ganymede, the largest in our solar system, possesses its own magnetic field, a clue that points to a layer of salty, electrically conductive fluid beneath its crust, likely a vast subsurface ocean. Its sibling Callisto, a battered and ancient world, also shows signs of a buried liquid layer, potentially separating its rocky core from its icy shell. At Saturn, the moon Dione, with its strange, wispy fractures, may have a global ocean deep within, kept warm by the same tidal forces that energize Enceladus. Even tiny, crater-scarred Mimas, which looks like the Death Star from science fiction, has recently revealed an orbital wobble that can only be explained by a sloshing, hidden ocean or an elongated, unfrozen core. This is not a collection of oddities, it is a census. The evidence is mounting that for mid-sized moons in the cold outer reaches of a star system, a subsurface ocean of liquid water is not a rare fluke. It may be the default condition, a natural consequence of their formation and the relentless gravitational kneading from their giant parent planets. Think of it like this. If you take a rocky body of a certain size, mix it with plenty of water ice, and then place it in the gravitational grip of a planet like Jupiter or Saturn, the physics almost demands an ocean. The tidal forces generate internal heat, and the ice acts as a perfect insulating lid, trapping that warmth to create a stable, liquid layer for billions of years. This realization is a cosmic game-changer. It means that in our solar system alone, the number of worlds with substantial bodies of liquid water might not be one Earth, but potentially a dozen or more. Now extend that logic across the galaxy. Every star like our Sun and every gas giant we have discovered around other stars could be surrounded by its own retinue of icy, ocean-bearing moons. The most common abode for life in the universe may not be a rocky planet basking in sunlight. It might be a dark, aquatic realm sealed under ice, orbiting a silent giant in the freezing black. We have been looking for puddles in the sunshine, while entire archipelagos of hidden seas were waiting in the shadows all along. But a planet's location and liquid water are only half the story. A deeper, invisible force may be the ultimate guardian of a living world. Drifting through space is a constant, invisible rain, a stream of charged particles blasted from stars known as the stellar wind. For life to thrive on a planet's surface, it needs a shield, a global force field generated from within the planet itself. This is the magnetosphere. It is a planet's magnetic personality, born from the churning of molten metal in its core. On Earth, that churning dynamo creates a powerful magnetic field that extends thousands of miles into space. This field acts like a cosmic deflector shield, bending the sun's deadly radiation and solar wind around our planet, channeling it harmlessly toward the poles where it creates the beautiful auroras. Without this shield, our atmosphere would be slowly, relentlessly eroded, stripped away atom by atom into the void, and the surface would be bathed in radiation that shatters complex molecules. We have a stark, tragic example of this next door. Mars. Billions of years ago, Mars likely had a global magnetic field, but its smaller core cooled and solidified, shutting off the planetary dynamo. Once the magnetic shield fell, the solar wind began its work. Over eons, it scoured away most of Mars's once thick atmosphere, leaving the thin, cold shell we see today. The water that once flowed on its surface either froze underground or was lost to space. Mars is a world that died from the inside out, a victim of a failed magnetic heart. This lesson is critical as we look at the most promising exoplanets, especially those orbiting red dwarf stars. These stars are not only prone to violent flares but also emit a relentless, powerful stellar wind. A rocky planet in the habitable zone of such a star would be under constant assault. Without a strong, global magnetosphere, any atmosphere it might develop could be stripped away in just a few 100 million years, leaving it a barren rock. A magnetic field does more than just protect the air. It also shields the surface from cosmic rays, high-energy particles from distant supernova that can damage DNA and prevent complex life from emerging. So when we dream of an Earth-like world, we must ask a new question. Does it have a magnetic personality? Is its core still hot and molten, spinning with enough vigor to generate that protective bubble? A planet can be the perfect size at the perfect distance with oceans of water and still be a cosmic graveyard if it lacks this invisible armor. The search for life, therefore, is also a search for planetary hearts that still beat with magnetic fire. We have just mapped a galaxy that seems overflowing with potential. liquid water may be the solar system's most common feature. The building blocks of life rain down from the stars. With hundreds of billions of planets in the Milky Way alone, and billions of years for life to arise, the cosmos should be a bustling metropolis of civilizations. Yet when we listen, we hear only silence. When we look, we see no great works. This glaring contradiction is the Fermi Paradox, named for the physicist Enrico Fermi, who, over a casual lunch, asked a devastatingly simple question. Where is everybody? If life is so easy, the galaxy so old, then someone should have gotten here by now. Their ships, their probes, their signals should be everywhere. Their absence is a mystery deeper than any ocean on Europa. After exploring 24 cosmic wonders, each a potential home, we must confront this great silence. One terrifying explanation is known as the Great Filter. This is the idea that somewhere between the emergence of simple life and the rise of a galaxy-spanning civilization, there is a step so difficult, so unlikely, that almost every world fails to pass it. It is a cosmic bottleneck. The filter could be behind us. Perhaps the jump from non-living chemistry to the first self-replicating cell is a miracle of such staggering improbability that it has only happened once in our galaxy, here on Earth. That would make our existence a breathtaking fluke, or the filter could be ahead of us. Maybe the development of complex animal life, intelligence, or technology itself contains a built-in self-destruct mechanism. Perhaps every civilization that reaches our level inevitably discovers the means of its own annihilation, through war, environmental collapse, or a technology we have not yet imagined. In this light, our list of wonders is not a directory of neighbors. It is a gallery of grave sites, worlds where life began but never made it past the filter. Another possibility is that we are simply not listening correctly, or they are not speaking in ways we can hear. A civilization just a few centuries more advanced than ours might use communication technologies we cannot yet detect, like neutrino beams or quantum entanglement. Or perhaps they have moved beyond broadcasting into space entirely. Their conversations contained within planet-spanning networks we would mistake for natural background noise. They might be all around us, silent and undetectable, like ants at the foot of a skyscraper, unaware of the conversations happening in the offices high above. Consider the worlds we have visited. A civilization on a tidally locked planet confined to a thin terminator zone might never develop astronomy or the concept of space travel. A species thriving in the global ocean of a Hycean world under a crushing sky might have no concept of stars or metal, their entire science built on fluid dynamics and deep-sea chemistry. Their greatness would be invisible to us. The most sobering answer to the paradox, however, is that complex, intelligent life is simply far rarer than we hope. A planet needs more than water and an atmosphere. It needs a stable star, a large moon to steady its tilt, plate tectonics to recycle nutrients, a magnetic shield, and billions of years of uninterrupted peace free from sterilizing asteroid impacts or gamma-ray bursts. When you multiply all those probabilities together, the number of Earths with civilizations able to look up and wonder might be vanishingly small, perhaps just one. In that case, the silence is not a mystery. It is the expected condition of the universe. We are not late to a crowded party. We are the only guests in a mansion of empty rooms, tasked with the profound and lonely responsibility of turning the lights on. The great silence is not an ending but a challenge. Our final cosmic wonder is not a place in the sky but a moment in time, the era we are now entering. For the first time in human history, we are not just dreaming of these alien worlds, we are building the machines that will visit them. The James Webb Space Telescope is our chemical detective, its golden eye already dissecting the light from distant atmospheres, hunting for the molecular whispers of water, methane, and carbon dioxide on worlds like K218b. Soon, the Europa Clipper will begin its orbital dance around Jupiter's icy moon, mapping its hidden ocean in unprecedented detail and tasting its surface plumes. On Titan, the Dragonfly rotorcraft will become the first vehicle to fly across an alien landscape, hopping between the methane dunes and dry lake beds of that frozen, organic-rich world. And on the horizon, missions like the Habitable Worlds Observatory are being designed with one explicit goal: to take a direct picture of a pale blue dot orbiting another star and analyze its light for the unmistakable signature of oxygen, water vapor, and perhaps even the reflected glow of continents. This is the pivot from speculation to exploration. Every mystery we have discussed, from the acidic clouds of Venus to the dark oceans of rogue planets, now has a spacecraft, a telescope, or a mission proposal assigned to solve it. We are sending our sensors across the solar system and beyond. The first definitive evidence of life elsewhere will not be a dramatic radio message or a sudden arrival. It will likely be a subtle but unambiguous chemical signal in a data stream, a strange imbalance of gases in an exoplanet's atmosphere that only biology can explain. Complex organic molecules erupting from Enceladus with a specific left-handedness, a pattern in the salts of a Martian rock core that mirrors the work of ancient microbes. That discovery could come next year or in the next decade from any one of the 24 cosmic addresses we have just toured. This is the profound hope that fuels the search. We are no longer passive observers of the cosmos. We are active participants in a grand investigation, testing our hypotheses against the reality of other worlds. The universe has provided the wonders. Now we are finally building the keys to unlock them. This grand tour has revealed a cosmos of staggering possibility, a gallery of worlds where life could wear 1,000 different faces. We have wandered from the methane rivers of Titan to the sulfuric acid clouds of Venus, from the global ocean churning beneath Europa's ice to the sunless seas of rogue planets drifting between the stars. We have imagined civilizations confined to eternal twilight on tidally locked worlds, and microbial ecosystems thriving in the radioactive warmth of a dwarf planet's core. The universe is not a barren void. It is a workshop of biology, experimenting with endless combinations of chemistry, energy, and environment. The most profound lesson is that life, if it exists out there, is almost certainly stranger than our boldest science fiction. It may not breathe oxygen, need sunlight, or even recognize the concept of a solid surface. Its home could be a pressurized hydrogen atmosphere, a deep volcanic fissure, or a floating droplet in an alien sky. Every strange world we have explored rewrites the definition of habitable, pushing the boundaries of where we must look. So the next time you stand under the night sky, remember this. You are not looking at a static tapestry of distant lights. You are gazing at a map of potential homes, each point of light a sun that could be warming a hidden ocean, drying methane shores, or illuminating the cities of a civilization we have yet to meet. The silence is not empty. It is patient, waiting for us to learn how to listen. Which of these cosmic wonders captured your imagination the most? Do you dream of the dark oceans of Enceladus or the eternal sunset of a Terminator world? Share your thoughts below and let us keep building this community of cosmic curiosity together. The search has only just begun.